Jai Shri Gurudev. Dear student, welcome to session 3 of module 2. In today's session, we will discuss about few examples on block diagram algebra. In the previous session, I had given you a brief introduction about block diagram representation, the type of the elements that is used for the representation of block diagrams. Along with that, we had learned 7 important rules which are used for the reduction of the block diagram into a canonical form to find the transfer function for the system. So let's continue with the same. So in today's session, I'm going to take up some example problems on block diagram algebra. So few examples are already discussed in the previous session. So here this is another example which is given to us. So for the given system, you need to find out the open loop transfer function, feed forward transfer function, control ratio, feedback ratio, error ratio, closed loop transfer function, characteristic equation, and closed loop poles and zeros if k equal to 100. And this is the block diagram given to us. So as you can see in the given diagram, these two blocks are connected in the cascade form. So you can apply rule number 2 here, and this takeoff point can be splitted for these two blocks separately. So this is the first thing what I have identified, and after this we'll apply the next two rules for this particular block and we'll try to simplify it. Okay, so you have to, the first thing when a given diagram, for a given diagram is that you need to identify the rules which need to be applied for the simplification. Now coming to one more example here. This is the block diagram given to us, and we are now supposed to reduce this. Okay. So you can observe here that you have G1 and G2, in between that you have a takeoff point. So I cannot simplify. So here you have H2 which is connected to a summing point. I cannot simplify. So if I move this takeoff point here, then these two will come in cascade and you can eliminate this loop. This is how you should identify which rules to be applied for that particular simplification. That is the first thing. Okay, so when I'm moving this takeoff point, so I moved the takeoff point. So here it is highlighted. So whenever I'm moving a takeoff point which is lying before a particular block, then what you can do is, so either you would have shifted it before or after. So what I did was I have shifted my takeoff point which was lying here before this block. So it is taken as H2 by G1. Then I have combined this G1 and G2 which is in cascade. Then what I did was, I'll be concentrating on these two summing points. Okay, here. Now this is a loop which you can simplify first. Now apply your feedback rule and try to simplify this. So it becomes G1 into G2 divided by 1 minus G1 G2 H1. After this, the G3 was in cascade with this particular block, so it got simplified as G1 G2 G3 1 minus G1 G2 H1. And now the last task is you can simplify this loop, feedback loop, as G1 G2 G3 divided by 1 minus G1 G2 H1 plus G2 G3 H2. Final step is you have one more loop and with a unity feedback gain. So here the gain is 1. So you can apply your 7th rule and you can simplify this. Okay. Now this is another example where you will be finding the transfer function of a block diagram. Now similarly here also you need to identify the rules which you will be applying it. So here also concentrate on this takeoff point and try to move here. It will solve one loop. Okay. That is what I told you. So this takeoff point you can shift, which is highlighted in gear. So moving a pickoff point A ahead of a block or your takeoff point. So I'm shifting it here. So please to observe here I'm moving it. So it is getting multiplied by G2. Then eliminate the loop. This loop which is marked with the pink circle can be eliminated once it is moved. as what? Here cascade and then parallel. Okay. Now, once this is done, I'm able to eliminate this as G2 plus G4 plus G2 G3. Then we need to think what is the next step. Now, if I move this takeoff point B here after this block, then I can simplify. That is what I'll do. So moving a pickoff point B which is behind a block after this block. Okay. So I'm moving it to the location C. So then in such case, this is taken out and it is shifted here. So it is getting divided by the gain what we have here, 1 divided by G4 plus G2 G3. Then now you can simplify this loop, feedback loop, with the gain, open loop gain as G4 plus G2 G3 and feedback gain as H2. And you can eliminate the loop, this loop, and this could be replaced as G4 plus G2 G3 1 plus H2 G4 plus G2 G3. Now further, now these two G1 and this is in cascade, so these two get multiplied, these two are getting multiplied and it is replaced as G1 into G4 plus G2 G3. Right? Now after this we have a loop for this. So once it gets eliminated, you will get a simplified feedback loop gain as equal to G1 G4 plus G1 into G4 plus G2 G3 divided by 1 plus G1 G2 H1 plus H2 into G4 plus G2 G3. Now we have one more loop with a unity feedback which you can simplify and you can arrive at your final result in the canonical form. So finally you can find your transfer function y of s by r of s as equal to G1 into G4 plus G2 G3 divided by 1 plus G1 G2 H1 plus H2 into G4 plus G2 G3 plus G1 into G4 plus G2 into G3. So this is how the final transfer function is obtained for the given block diagram. I hope you have followed. Now coming to a system with multiple inputs. Okay, so you need to find out the transfer function and the output C due to the input R and input U. Okay, so there are two inputs given to us, U and R. So initially when you are finding the response for the input R, you need to take your input U as equal to 0, and once this becomes 0, you can reduce your system as equal to directly as you will remove this. So once this is removed, these two get directly connected, so it can be taken as G1 G2 and you have a feedback loop. So finally you can get the output response U of R as equal to G1 G2 divided by 1 plus G1 G2 into R. And similarly, when you are finding the response with respect to the input, second input U, then you have to take R as equal to 0. So when R is equal to 0, this is how your block diagram gets reduced, and if you rewrite it, this is how the system looks. Now we have two blocks in series, or you can consider this to be in cascade, with one forward path gain as equal to G2. So minus 1 into G1 becomes minus G1, so that this plus becomes minus here. Okay, and it becomes negative feedback. So in such case, you have the transfer function as equal to G2 divided by 1 plus G1 G2, and your response with respect to the input U is represented as CU, and it is taken as G2 divided by 1 plus G1 into G2 into U. So problems like this could be given with multiple inputs also. So this is the final output response what we are getting for both the inputs. So total output response C is equal to CR, response due to input R and response due to input U. So just add the two responses, that becomes your final response C for the system. So this is called as your total output response when you have multiple inputs. For example, if I had one more input, I would have taken one more response for that particular input by making the other two inputs as 0. Now this is an example what I was talking about with three inputs, that is R, U1 and u2. So in the first case, I am making u1, u2 as equal to 0 and I am finding the response for the input r. So when these two are removed, g1 comes in cascade with g2 and h1 comes in cascade with h2, and your response, output response, is taken as g1 into g2 divided by 1 plus g1 g2 into h1 h2 into your input r. This is the response for the input r. Similarly, in the next case, when I am finding the response for u1, you have to take r and u2 as equal to 0. So when these two are made as 0, your block diagram gets simplified like this. And when you rewrite the same block diagram, it looks like this. So g2 is in cascade with h1 h2, so you can take this as g1 h1 h2, and this is your forward path gain, and your response due to the first input is taken as c1 g2 divided by 1 plus g1 into g2 h1 h2 into u1. This is when u1 is active and the other two inputs are 0. Now similarly, the same thing should be repeated for the last case, where you will take r and u1 as equal to 0, u2 will be active now. So this is how the diagram looks. Now if you rewrite the diagram, we have h1 g1 g2 in cascade, so you can just combine them as g1 g2 h1, and this is your feedback h2, so that your response, you will be getting it as g1 g2 h1 divided by 1 minus g1 g2 h1 h2 into your given input u2. And similarly, you can take a superimposition of all the inputs together and you can add them. So by superposition of the total output, you can take your C as equal to, in this case, as equal to response due to the input R, response due to the first second input u1, and response due to the another input c2. So totally you need to add, and if you simplify, your final output response is taken as g1 g2 r plus g2 u1 g1 g2 h1 u2. So we have multiplied the corresponding inputs here, 1 minus g1 g2 h1 h2. So this is how the total response for a system with multiple inputs could be analyzed for a given system using the block diagram reduction rules. I hope you have followed all the three examples which is quoted in today's session. So if you, I have taken three different examples. First one was very simple, where we were applying the basic rules, and then in the second problem you have learned how to apply the other rules like shifting the takeoff point and summing point, and then you have analyzed how to reduce such complicated diagrams by identifying the suitable rules. See, basic thing what you need to remember in block diagram reduction is you should know what rule you have to apply for what condition. So if you are clear about all the rules and if you know how to apply the rules for a given diagram, then block diagram simplification becomes very easy. So try to recall all the four rules. The first rule is your cascade rule. Second rule is your parallel rule, where you will be adding or subtracting your responses. In the first rule, you will be multiplying your gains, and in the third rule, you will be shifting your takeoff point before or after a block. And in the in the third and fourth rule, takeoff point shifting is learnt. In fifth and sixth rule, you have learnt about shifting of a summing point before and after a block. And in the seventh rule, you have learnt about elimination of the feedback loop with positive and negative feedback. So in today's session, I have taught you the few important example problems on block diagram reduction rule, and you have learned how to find out the transfer function for a given block diagram by applying the suitable rules, and you will try to reduce the given complicated block diagram into a simple form by using the suitable rules. And in the second case, you have learned how to reduce the block diagram if multiple inputs are given. So what we did in the multiple inputs block diagram representation is, whenever we are finding the response for one particular input, the other input should be made as equal to 0. Like this, you have to keep one input and the remaining input should be made as 0, and same thing should be repeated. Now once the response for all the inputs is obtained, then you have to summate all the output responses what you have got for the different inputs, and then you have to superimpose all the responses and you have to find the total response for the system. So these are the references from which I have taken the problems. So you can just further refer few more books and try to solve the similar block diagram problem. See, the main thing what you have to learn in block diagram is you have to practice. So try to identify the rules. That is the first major thing what you have to know in the reduction rules. So learn the rules in a proper way. Try to remember the rules. So majorly you will have a confusion in your I think third and fourth and fifth and sixth rule you will have a confusion, because there you will be shifting the takeoff point, and in another rule you will be shifting a summing point. So just remember in takeoff point when you will multiply the gain and when you will divide the gain. And similarly in summing point also you have multiplication and division of the gain. So but you should know what is the criteria you are following, whether you are moving a takeoff point before which was lying before a block, or you shifting a takeoff point which was lying after a block. So just try to remember the position of the takeoff point and the summing point before shifting it. And do not, most of you will forget to multiply the gains for the branches which you are moving with respect to takeoff point and summing point. So do not do that mistake. So please concentrate on the rules and learn the rules properly so that you can analyze or reduce the system to a simplest canonical form to find the transfer function for a given complex block diagram. See, the main idea behind this reduction rules is, see, if the system becomes complex and if you use more elements to build a particular system, then it won't become cost effective. The cost of that particular system is always, it increases. So always our main focus when we are building the system is on miniaturization. We'll try to make the system as simple as possible, as small as possible, right? So simple example is we had a big telephone decades back, and that is just replaced with a small cell phone. So miniaturize is the main thing on which the industry is working. So whenever you want to build any system, so you have to consider these three things before building any system, that is area, cost and power utilization. So whenever you try to reduce the area, obviously the cost becomes less and the power consumption also reduces. So that is why this is just an example what I'm quoting. What is the importance of reduction of a particular system into a simplest form. So I hope today's session was very informative. So try to practice more number of problems on this particular topic so that you will have a control over your reduction rules. Thank you one and all for joining the session. Have a nice day. Jai Shri Gurudev.